चाय के बाद next time maybe. Okay.
Hello, am I audible?
Yes, sir.
So Ruchi, I think system is our system is set. So whenever you are ready, we can start the session. Okay.
Yes, sir. We'll start in 3 minutes. I request all the participants to kindly mute their mic. Am I audible?
Yes, madam.
Okay. So, hello everyone. Good morning. Welcome to the technical session on basics of self-balancing robot. And this session will be taken by Avinash Dubey, who's doing his PhD from control system in electrical engineering, and Avijit Pandey, who's doing his MTech from ET department from IIT Bombay. Okay, so I'll hand over the stage to Avinash sir and Avijit sir. So let's get on it.
Thank you, Ruchi. So let's start with the basics of self-balancing robot. I hope I'm audible, right? If yeah. So what we will learn here is like we will see the two control techniques which we usually use. One is the PID, which is very usual. Everybody is using the PID control in one or the other way. And then we'll see the LQR control technique. and the advantages we have over the PID control techniques. So before that, I like to specify that we will not go deeper into the theory part. We will try to just analyze that how we can build the self-balancing robot. We'll see the derivation and then some implementation of the self-balancing robot. So we'll confine our whole theory in designing a self-balancing robot. Fine. So let's moving further. Yeah. So our agenda for the discussion will be like we'll see that there are two types of self-balancing robots which we can make, and we'll see that what PID control technique is if you are not aware, and what advantages this PID control technique brings. Then we'll look into the state space modeling, and then we will see that how to proceed from PID control technique to the LQR control technique, where we will need some mathematical modeling. Since the usually systems are nonlinear in nature, so we will have to linearize the system, check for its stability, and more precisely stabilizability. And since we are implementing the most of the things on the controllers which are discrete in nature, so we will have to discretize our system also. And then we'll see some basics of LQR control technique, what to choose and why to choose. And then Avijit will handle the other part of the session, that is dealing with the CoppeliaSim and how to choose the right hardware for your self-balancing robots. So moving ahead, we will start with the first type of self-balancing robot, where we balance the our robot via the driving wheel itself. So to present that, I'll show you this video. Is the video visible to everyone? Yes, sir.
Yes, sir.
Okay,
Yes, sir.
okay.
Yes, sir. Yes, sir.
So this was the first type of self-balancing robot, where the balance was done using the driving wheel itself, and this was introduced in our e-Yantra. Hello, I'm getting echo. Yeah, so this was introduced in our e-Yantra robotics competition.
Sir, there's echo.
Yeah. So I hope it is not, there's no echo now. Fine.
Yeah.
Yeah. So this was introduced in our one of the themes in e-Yantra robotics competition in 2019, where we introduced it with the name of biped petrol. Now we'll go to the second type of self-balancing robot, which we introduced in last year in our theme known as dairy bike. Yeah, so you saw that here the balancing was done using the reaction wheel concept. So this is the main difference between the two types of self-balancing robot, where in one you are using the driving wheel as the for the balancing, and in the other you are using the reaction wheel for the balancing. But inherently the concept underlying both of them is inverted pendulum. So we will move further and see that how this concept helps us. But before that, we'll go into the PID control technique, which we are usually used to use in our control design techniques. So what PID control technique is? So like we have a plant where the input U is given and we have some output Y, and we have some reference input RT, which we need to track, right? Our YT should follow RT. So what we do is we take the difference of our measured output with the reference input, and we take the error out of it. And then based on our error, we apply our control technique so that our UT is in such a way that it gives you the desired output. So our main objective is to bring this error to zero, right? So for that, we use three types of gains, which is called proportional gain, derivative gain, and the integral gain. So KP is known as proportional gain, integral is KI is known as integral gain, and KD is known as the derivative gain. So how does this work? So we first start by introducing the KP, which is the proportional gain, which is proportional to the error of the error in the system. So we measure the error and we directly multiply the error with some proportional gain. And if the error is large, the proportional gain is large. So the control input is accordingly adjusted so that you can get the desired input UT for the plant. So we started by introducing the proportional gain till there is an oscillation. There is an oscillation in the system. Once the oscillation starts, then we try to bring the KD into the picture, which tries to reduce the oscillation. Fine. So KP to reach up to the desired output, but once it reaches the desired input, we further increase so that a little bit of oscillation starts. So we are moving about our desired inputs. Then we introduce the KD, that is proportional gain, which is proportional to the rate of change of error. Sorry. Yeah. So rate of change of error, and then finally, after applying the PD controller, we still have some leftover error in the steady state. So to reduce that steady state error to zero, we introduce the integral gain. So this is how our PID control technique works. If you notice that it is mostly like you don't need the information of the transfer function of the plant itself. What you need is you need a measurement of your output, the reference input which you want to track, and then calculate the error and feed the and design your controller accordingly. So you don't need much information about the plant or system here. So this is the advantage which you get in the PID control technique, that you don't need much of the information of the plant. But the problem with the PID control technique is you don't know, given the performance parameters of your performance specification for your system, you don't know that like there is no one gain to tune so that you get your desired performance. So you have to tune from in all the three parameters like KP, KI, and KD. All three work simultaneously to achieve a performance specification. So the tuning part becomes very difficult in a PID control technique. And also, as the environment changes or the system change, the PID control technique needs to be retuned. So every time you change the environment, you have to retune the PID. It does not work in every possible environment. So to come up with a solution for that, we will need to know about the plant behavior, and we need to use the mathematical modeling of the plant, so that we need the model of the system. So for that, we will first try to introduce what state space modeling is. So state space modeling is basically you have some desired variables in your system which you want to know. Those variables are called the states of the system. Then based on those states of the system, you represent your whole system in form of linear differential linear equations, which is x dot equals to ax plus bu, where x is your state of the system and a is a system matrix, and ut is your input to the system, and b is the input. B is known as input matrix. Y is your output of the system, and y equals to cx plus du, where c is the relation of y with the um, states, output with the states, and d is the feed forward matrix which relates your output to the input. So these are the different dimensions of the system. Like if you have n variables, n state variables, then xt is an element of Rn, and so accordingly, A will be a n cross n matrix denoted as real Rn cross n, an element of Rn cross n. And similarly, if there are m inputs, then B is an element of Rn cross m. So these are like your general state space representation for the linear invariant system. If your system is non-linear, then the expression can vary differently. So we are just trying to represent it through a function like f of t cross xt as the x dot, and y as the h, some function h as a function of time, your states, and the input. So this is a typical representation of a non-linear system. So why we are going for this non-linear representation? Because usually you try to represent your system with a linear equation, but the fact is that every system usually are non-linear in nature. So when we derive the first equation, it is usually non-linear in nature. Then we try to bring it into a linear form so that we can work with it, because we are only good in linear control strategies. Although non-linear controllers are there, but most of the time we used to work with the linear controllers. So we need to bring our system into linear form. So what are the various steps to follow? First, this is one of the way. This is known as the Lagrangian mechanics, where you try to bring the energy picture into the energy picture of the system to model your system. So how do you do? You first find out the kinetic energy and potential energy of the system. Then you find a function which is known as Lagrangian function, where you take the difference of kinetic and potential energy. Then you determine the states of the system. Usually the states of the system are denoted by two things. One is the position vectors and another is the velocity vector, known as q and q dot. Then we get this Euler-Lagrange equation, which is represented by this equation, d by dt of del L by del Q dot. Here you can see that Q dot is here, which is the velocity vectors of your states, minus del L by del Q. Q is your position vectors, and that is equal to the torque or the force acting on the system. So where F is non-constant force in case of linear motion and torque in the rotational motion. So force or torque. Now you solve this equation, you get certain equations which are non-linear in nature. So representing again that thing into the non-linear formula, we can say that x dot equals to some function of time, state, and input. Now this is a non-linear equation. So what we need to do is we need to linearize the system. How do we linearize the system? We find the Jacobian of the system. Now this is the formula for the Jacobian. That is a partial derivative of each functions. Like there will be, this function will be like multiple functions will be there, f1, f2, which is stacked in a column. So we will try to differentiate each function with respect to each of the states, and this is represented as a matrix. This JA is known as the A matrix with respect to the states, and this B is when you differentiate it with respect to the inputs, you get the B matrix. Fine. Now, to find out the A and B matrix, one more parameter you should know, that is your equilibrium point. Now, how the equilibrium point is defined? So equilibrium point is a point where if you don't apply any input to the system, your states are not going to change. That is, the state becomes constant. And how do you represent that mathematically? X dot equals to 0. If x dot equals to 0, what does that mean? That x equals to constant. X equals to constant means your states are constant. That is, there is no change in state unless you apply some input to it. Fine. So to find equilibrium point of the system, that are the stationary points of the system, you need to equate x dot equals to 0, where x are all the states of the system. So the condition in which all the states of the system, the derivative of all the states of the system becomes 0, that point is known as equilibrium point. So so being a nonlinear equation, you can have multiple equilibrium points in the system. And each equilibrium point can behave differently. Some of them can be stable, some of them can be unstable, some of them can have oscillation, and so on. So A and B matrix will also depend on what your equilibrium point is. That is, you're linearizing your system around equilibrium point. So it is not a global linear system. Your system does not become linear. You are linearizing in a small extent around your equilibrium point, where you assume your system to behave like a linear system. So to find out that the linear region, you need to plant your equilibrium point in this particular Jacobian, and accordingly you will get different A and B matrices depending on your different equilibrium points. So for each equilibrium point, you will get different A and B matrix. Now, the next point will become how you determine whether the particular equilibrium point is a stable equilibrium point or unstable equilibrium point. So for that, you will find out the eigenvalues of the Jacobian, and those eigenvalues of the Jacobian, if in continuous time domain, that should be in the left half of the complex plane, right? If you are aware of the control system, in the continuous time domain, left half of the poles should the poles for a stable system should be in the left half of the complex plane. So basically, the poles of the system are represented by the eigenvalues of the matrix. So the eigenvalues of the Jacobian matrix A should be in the left half if it is in the continuous time domain. Now, if you discretize your system, the system changes into the discrete time domain, then the imaginary line in the complex plane gets converted to the unity circle in the Z plane. So the condition translates to that for a discrete time stable system, your eigenvalue should be inside the unit circle. And if it is outside the unit circle, your system becomes unstable. So for stability in the continuous time domain, your eigenvalue should be in the left half of the complex plane. And for the discrete time, it should be inside the unit circle. Fine. Now we will go to our self-balancing robot and try to derive these equations. For that, I will have to switch the system. So just give me a minute.
Hello.
Yes.
Sir, good morning.
Good morning.
I am Dr. Ghanshyam Singh from Telangana State, sir. I have a
Yes.
small doubt, sir.
Yes,
Sir,
sir.
you are telling equilibrium system, a value of the state, variables, the state do not change.
Yes.
Am I right, sir?
Yes, yes. States
Then
does
one
state become
doubt.
constant.
Equilibrium state in control system, sir.
Equilibrium points of the system. Yeah.
Of the system XT.
Sorry, I lost you. Can you repeat?
We are having error ET of the state XT in between the target value and actual values.
Hmm.
How can we control, sir? What is the equilibrium control system?
Sorry, can you repeat? I lost you in between.
Okay, sir. Okay. We are having error ET of the state XT
Yes.
in between the target value and actual value when zero every time.
Yes. Yes, that is our objective. So equilibrium point does not depend on your control techniques. Equilibrium
Yes, sir.
point is inherent of inherently lying inside a system, right?
Yes.
A system will have certain equilibrium points where if you don't apply any inputs, it will remain where it is, right? Those
Okay.
points are called equilibrium points. So basically, as a definition, if your input should be 0 and your desired states, the derivative of those states becomes 0. Simultaneously, all the derivative of the states become 0. Those points are called the equilibrium points. So right now we are just going by the definition. Now controlling the error to 0 is what is usually desired in your control system. You want to bring the error to 0. So that is why you use the different types of control technique. One we have already discussed, that is PID control technique, and the other we will be discussing soon, that is LQR control technique.
It means, sir, its time derivative corresponding to each order are equal to 0.
Yes.
Okay, sir. Thank you. Thank
Yeah,
you,
so
sir.
that is the definition of the equilibrium point. Now the system is inherently non-linear in nature. So what we are trying to do, around that equilibrium point, we are taking a small ball, very small ball, which we know in our control theory as a epsilon ball. Okay, we assume that epsilon ball to behave linearly, although the system is non-linear in nature. But if we take a very small region around equilibrium point, we assume it to behave linearly. And now we design the control technique in such a way that system will not go outside this linear region. If it goes beyond this linear region, the system, your controller may fail. Okay, so it is designed in a very small vicinity of the equilibrium point. So that's why equilibrium point becomes very crucial in nature. Okay, shall I move ahead?
Yes, sir.
Presentation. Yeah, so we will go with the derivation. Okay, I hope the screen is visible to everyone. Yeah, so we will assume our system to be something like this. This is your center of mass. Okay, and this is your wheel. This is a very what I'll say, that miniaturized version of your self-balancing robot. This is like very simplified view of self-balancing robot. Your wheel and your whole body uh, concentrated around some point that is called a center of mass. So we will say MC as the center of mass, and this radius of the wheel as RW. Okay. So now if my body moves a bit towards, so this theta, which it makes with the vertical, I'm calling this as theta C. And similarly, if my wheel has been rotated by certain angle, I'm calling this wheel rotation as theta W. So theta W is the wheel rotation. Theta C is the angle by which body has moved, body has rotated. Okay. So what my states are? My states are theta C, theta W, theta C dot, and theta W dot. That is the angular velocity of the body, angular velocity of the wheel, angle of the body, and the angle made by the wheel. So now, how the center of gravity moves? It has two components. Like if it is tilted at an angle theta C, now it will have two components. One will be is like the x component, and another will be like z component. If I assume this to be LC, that is the length of the pole, then XC will be RW theta W, that is how much it has rotated because of the wheel, plus LC sine theta C, the X component of this L sine theta, this component. This is L sine theta, and because of the wheel also it has moved certain angle, that is theta R, certain distance, that is theta R. Similarly, in the Z component, it is LC cos theta C. Correct? I hope this is clear. Now, if I talk about the wheel, how the wheel has made the motion, so it will also have some component X and Z. There will be no Y component because it is two-wheeled self-balancing robot, so it cannot move in the Y direction. It can only move in the X direction, and because of the inclination, it can move in the Z direction also. Now, since wheel is at a specific height, it does not move in the Z direction, so their Z component will be 0. And same distance will be moved by the wheel also, so theta R. Now, these are the positions of your wheel and position of the body, right? Now, we will try to form the Lagrangian function. I can delete this, right?
Can you just wait a bit?
Yeah.
So that we can just grasp what is the center of the first part. Can you explain XC and ZC?
Yeah. So basically, your center of mass, if it rotates by an angle theta C, so where and your wheel has rotated by theta W, right? There are two rotations which you are talking about, that the wheel has rotated by an angle theta W, and your center of mass, your body has tilted by an angle theta C. So how is your center of mass, what is the position of your center of mass? Now, center of mass will have two positions. One is in the X direction, one is and another is in the Z direction. Now, how does it move in the Z direction? That is given by this L cos theta. This is the vertical direction, right? L cos theta is your Z domain, Z distance, right? And
Fine.
and Z sine theta is the y, this X component. But apart from this L sine theta, it has also moved because of the wheel, because wheel has moved forward, right? And how much wheel has moved? Wheel has moved theta R. Correct? That is the arc made by the wheel if it rotates by theta degree, right?
Got it, sir.
So this is the X component of your body, and this is the Z component of your body. Now, wheel's Z component is not going to change. It will remain at the same height, correct? So Z component of the wheel is 0, but the X component of wheel is same as the X component like theta R, right? This is clear?
Yes.
Fine. Now, if you remember the Lagrangian function which we made, that was made as the kinetic energy minus potential energy, correct? Now, here we have two things. One is the wheel, another is the body. So now we will split these things into two parts. One is kinetic energy of the body plus kinetic energy of the wheel minus potential energy of the body minus potential energy of the wheel, correct? Now, one more thing you notice, in the self-balancing robot, we are using two wheels, correct? So kinetic energy of the wheel will be multiplied by 2 because there are two wheels. So kinetic energy of each wheel will get added. Similarly, 2 times of the potential energy of the wheel also. Now, so this Lagrangian function becomes half mv square, right? kinetic energy of the body plus this is translational kinetic energy. Remember, there will be two types of kinetic energy. One is rotational kinetic energy, another will be translational kinetic energy. So this is the translational kinetic energy, half mv square plus half I omega square. Omega is theta c dot square. Correct? Now 2 times of half mass of wheel into velocity of wheel square. So basically this will get cancelled out, plus half 2 times of I omega square for wheel. Correct? Now if I talk about the potential energy of the wheel, since the z component is not changing, so potential, and we take the reference line as the line joining the two wheels, the center of the two wheels, the potential energy of the wheel becomes 0. So we are only left with the, sorry, please mute if you don't have to ask questions. So mass into mg and h, which is zc, right? So this is the Lagrangian function. If I, hello, Ruchi, if you can mute, I'm getting the noise from somewhere.
Sir, I'm just muting everyone and then you can unmute yourself.
Okay. Shall I start? Yeah.
Yes,
So
sir.
yeah. So now I'll expand this just to show that how this corresponds to your states of the system. Remember, the states of the systems are theta c, theta w, theta c dot, and theta w dot. These are our states of the system. Now the Lagrangian becomes half mc. Now vc has two component. Remember, vc has two component, xc dot and zc dot. So this becomes r square theta w dot square plus lc square theta c dot square plus 2 rw lc theta w dot theta c dot cos theta c. You can verify later, but this will be the expression half ic theta c dot square, half ic omega square, which is already been there, plus mw vw square, which is rw square theta w dot square plus iw theta w dot square minus mcg lc cos theta c. Fine. Now this expression of Lagrangian is written as a function of your state variables. Correct? Now, if you remember, what you need to do is you need to find the Euler Lagrange equation. For that, you need partial derivative with respect to all the state variables. Pandey? Oh, check. Yeah. So what you need to do is del L by del theta W. You need to first find out this. Now, if you see the Lagrangian function, if you remember, this is partial derivative. So theta, any component of theta W is not present in this whole Lagrangian expression, if you see carefully. So this del L by del theta W becomes 0. Remember, this is partial derivative. Theta W dot does not count because it is already a derivative, it is already a state, and you just need to find out the components where there is theta W. Now then, second is del L by del theta C. Now if you see that there is component of theta C here also, yeah, two places. So now if you take the derivative, this become mcg I'll just write the expression, you can verify it later. MC LC RW theta W dot theta C dot minus G sine theta C. You can verify that this will come out to the same. Now taking this derivative with del theta W dot, you will get 2 theta W dot IW plus MW RW square plus MC RW square by 2 plus MC LC RW theta C dot cos theta C. Similarly, last component del L by del theta C dot, which becomes theta C dot IC plus MC LC square plus MC LC RW theta W dot cos theta C. Now you got all the partial derivatives. Now what is the next step? You just see the Lagrangian equation, what it was. Del L by del Q, del L by del Q dot. These four equations you have got. Now you need to take the full derivative of the partial derivatives with respect to the Q dots. That is theta C dot and theta W dot. So for these last two equations, del L by del theta W, this equation and this equation, you need to take the full derivative also. So I hope that I can delete this one. Blackboard is full, so I am erasing the Blackboard. You will get it on the YouTube live, so that's not issue. Yeah. So now we'll take the full derivative d by dt of del L by del theta W dot, which you will get 2 theta W dot double 2 theta W double dot IW plus MW RW square plus MC RW square by 2 plus MC LC RW theta C double dot cos theta C minus theta C square sine theta C. You can take, you can do the derivation by yourself and you will see that you will get this expression. So that's why I'm not showing the steps, but this is the expression you will be getting. Similarly, del theta C double you will get theta C double dot IC plus MC LC square plus MC LC RW into theta W double dot cos theta C minus theta W dot theta C dot sine theta C. This is the equation you got by d by dt of del L by del theta W, d by dt of del L by del theta C W. Now, since you have got all the expressions, now what you have to do is you have to find this thing minus del L by del theta W and equate it with the torque 1. which is the wheel's torque, the torque applied on the wheel. Now the second component is this one. Sorry. Equals to, now what is the torque on the body? Now listen carefully. If your wheel is rotating in the forward direction, your body will move in the backward direction. So if the torque applied on the wheel is T1, the torque applied on the center of the body is minus T1. So this equals to minus T1. Now you get this two expression. You can find out theta C dot double dot and theta W double dot. So I'll just write those expression and you can find that out. Okay. Yeah. Theta W double dot becomes K2 T1 plus K2 K3. I'll explain what K2 K3 is. K1, K2, K3, K4, K5, what these things are. Sine theta C minus K3 T2 cos theta C minus K3 K4 into 0.5 sine 2 theta C divided by K1 K2 minus K3 square cos square theta C. Now K1, K2, K3, K4, even K5 will come. So these are the constants dictated by the system parameters like radius of the wheel, mass of the body, inertia of the body. So I have taken all those constant things as K1, K2, K3, K4. You'll find the expression, you will realize that these are the constants. And I have just taken the inputs and the states as it is. So this is the expression you get for theta W double dot. And similarly for theta C double dot becomes K1 T2 plus K1 K4 sine theta C minus K3 T1 cos theta C minus K3 square 0.5 theta C dot square sine 2 theta C divided by K1 K2 minus K3 square cos square theta C. Now you got the theta W double dot and theta C double dot. Now I'll come back to my states. What was my state? My states were theta W dot, theta C and theta C dot. Correct? These are my states X. So what is my X dot? My X dot is theta W dot, theta W double dot, theta C dot and theta C double dot. Now for finding out the equilibrium point, my X dot should be equal to 0. Correct? So what does I get from here? From here I get theta W dot equals to 0, theta C dot equals to 0, theta W double dot equals to 0 and theta C double dot equals to 0. Now theta W dot equals to 0 and theta C double dot equals to 0 is very straightforward. Now theta W double dot equals to 0 and theta C double dot equals to 0. For that you will have to equate this equation equal to 0. Correct? Equal to 0. Now one more thing in the finding out the equilibrium point was that the input should be 0. Otherwise it will not remain in that equilibrium point. So this T1 becomes 0, this T2 becomes 0. Correct? Since theta C dot equals to 0, this also becomes 0. So what is remaining in theta W double dot? K3 K4 into 0.5 into sine 2 theta C. Now just by the visual inspection you can get that if sine 2 theta C equals to 0, this theta W double dot equals to 0. That means that theta c equals to n pi, correct? 0, pi, 2 pi. These are your equilibrium point. So if I go in between 0 to 2 pi, so my two equilibrium points are 0 and pi. Theta c equals to 0 and pi. Similarly, if I put theta c double dot equals to 0, again T2 is 0, T1 is 0, theta c double dot equals to 0. So K1, K4 sine theta c. Again, it depends on the theta c. That means that theta c equals to n pi is equilibrium point for making theta c double dot also equal to 0. So my condition for theta c equals to is 0 and pi. So what is my equilibrium point now? Delete something. So what is my equilibrium point now? To make x dot equals to 0, that is theta c dot, theta c double dot, theta w dot, and theta w double dot equals to 0. My x, which is theta c dot, theta w, and theta w dot, is equal to, now theta c has two values, right? So I'll get two equilibrium point. One is 0 and one is pi. Theta c dot equals to 0, theta wheel is equal to 0, and theta w dot equals to 0. These are my equilibrium point, correct? So I get two equilibrium point. One is 0, 0, 0, 0. One is pi 0, 0, 0, 0. Now, after that, you can find the Jacobian. So for Jacobian, what you'll need to do is differentiate each of the theta w double dot, that is the f1, and theta c double dot, which is f3. F2 and F4 is already theta c dot and theta w dot, which will become like your already they are in the states. So I'll need to erase something. So now x dot, which is equals to theta c dot, theta c double dot, theta w dot, theta w double dot equals to something into x, theta c dot, theta w, and theta w double dot. Correct. Now theta c dot equals to 0, 1, 0, 0. This is very straightforward. Theta c dot equals to theta c dot. Similarly, theta wheel dot equals to theta wheel dot. Now this theta c double dot and theta w double dot, you will have to find out using the equilibrium point. That is del theta c double dot divided by del theta c. Del theta c double dot divided by del theta c dot. Del theta c double dot divided by del theta w, and del theta c double dot divided by del theta w dot. Similarly, this one, del theta w double dot divided by del theta c, del theta w double dot divided by del theta c dot, del theta w double dot divided by del theta w So these equations you will have to evaluate because theta c and theta w double dots have certain equation. You will need to take partial derivative. You will get some expression in the form of cos and sine, and then you will put the equilibrium point here. You put the equilibrium point in this particular expression, and then you will get A and B matrix. So for our equilibrium point, I'll tell you what the A matrix looks like. Our A matrix given, so there is a shuffling in the states, or the order of state which I have chosen. So my state is theta w, theta c, theta w dot, theta c w, theta c dot. If these are my states, my A matrix will come out to be 0 0 1 0 0 0 0 1 0 minus k3 k4 divided by k5 0 0 0 k1 k4 by k5 0 0. These are my A matrix corresponding to this order of the states. Fine. Now if you see carefully, our expression here showed us that it only depends, the theta w double dot and theta c double dot only depends on theta c, nothing else. There is no other states involved in this particular expression. In this two expression, it only depends on theta c, which is also you can realize with the matrix A, that it only depends on the theta c, the second variable. Okay. Similarly, the matrix B, which is proportional to your input, will come out to be 0 0 k2 plus k3 by k5 and minus k1 plus k3 by k5. These are the B matrix. So now you got the A and B matrix for the system. Now after you get the A and B matrix, you need to determine the stability of the system. Since you have already put the equilibrium point, you have the numerical value for your A and B matrix. Now you can find out the eigenvalues of those matrix. If those matrix, if the eigenvalues of those matrix, that matrix A is in the negative half, it is stable. If it is in the positive half, it is unstable. Now if you see, there are two equilibrium points where theta c, what is theta c? Theta c was your body's angle, right? If so, there are two equilibrium points. One is theta c equals to 0, that is this theta c is vertically aligned, and another was theta c equals to pi when it is vertically downwards. Now if you can see, this is like a normal pendulum, right? And a normal pendulum is when theta c equals to pi. This is like an inverted pendulum, normal pendulum, and it is a stable equilibrium. So by intuition only, you get that the theta c equals to pi is a stable equilibrium, and theta c equals to 0 is upward. And you know that if I leave something in the upward position, it is going to fall down. So by intuition also, you can see that theta c equals to 0 is your unstable equilibrium point. So in this exercise, I'll just summarize what you have done. You have found out the kinetic energy, potential energy, got the Lagrangian, got the Euler-Lagrange equation by differentiating the equations, and then you find out the equilibrium point. Putting those equilibrium point, you have got your A and B matrix. So now you have a linear system in which you already know x dot equals to ax plus bu. You already know A and B matrix. Yeah. Somebody asking anything? And y equals to cx plus du. So d is assumed to be 0 here. There is no feed forward again. And c I assume here as the identity matrix because I am measuring every state. If some states are not measurable, then you will have to get the observer. You will have to observe those states. So here I am assuming all the states are measured states. So the C here is identity matrix. So before I design a controller, I need to ascertain that the eigenvalues, if there are some unstable eigenvalues, I'm able to stabilize that. What do I mean by that? I find a controllability matrix C, which is given by B, A, B, and so on up to A n minus 1B. I hope it is all visible. I'll write it somewhere else. So now you have got A and B matrix. So you find out the controllability matrix, which is given by B, A, B, and so on up to A n minus 1B, where since you know that A is a square matrix of n cross n matrix, so A n minus 1B, you will find out this matrix up to A n minus 1, and you will find out the rank of the matrix. Rank of the matrix. Rank of the matrix usually means that how many independent columns or rows you have. For a square matrix, rows and columns are equal in nature. So if you have a full rank, like if it is a 4 cross 4 matrix, full rank means that there are 4 independent columns, so that each of the columns you can independently control. So if that's the case, if your system has a full rank, controllability matrix is full rank, then the system is called to be controllable, and you can stabilize that. If there is some eigenvalues which are not controllable, then it is a problem. You might not be able to design the controller. Then there is something called stabilizability. You analyze whether the unstable eigenvalues, whether you can control it or not. That's beyond the scope of this our design, because here usually what you will get in the self-balancing robot is the controllable matrix. So you can design the controller for it. Now we will go for the discretization purpose. Why we go for the discretization? Because your system is, although you have designed it for the continuous time domain, you have find out everything till now in the continuous time domain, but you are going to implement it on the microcontroller. Microcontroller does not work in the continuous time domain. It is discrete in nature. Okay, so you need to discretize your system as well, so that it can act according. You can design a controller on your microcontroller. So there is a inbuilt function in Octave or MATLAB, whatever you are using, which is called C to D, that is continuous to discrete time converter, where you feed your A, B, C, D matrix in the continuous time domain, and you get a discrete time ABCD matrix. Your system matrix is converted to the discrete domain ABCD. Just note that in the continuous time domain, your eigenvalues were placed in the left half for it to be stable. Now, when you have a discrete time matrix, you will have to check the condition as inside the unit circle. The eigenvalues should be inside the unit circle to be system to be stable. So that's the difference. Also, you need to determine that what is the sampling time. Sampling time means you will be taking the samples of your system, right? And that for that you will need some sampling time. So for discretization of the discretization process, apart from ABCD matrix, that is system matrices, you will also need to determine what is your sampling time. This is something which is in user control, so you can determine, but just you need to ensure that you make it a constant sampling time for it to be uniform. Otherwise, for non-uniform sampling time, we will have to take another measures. Usually we use uniform sampling. So while programming, you need to somehow, yeah.
Excuse me, sir.
Yes.
For uniform sampling, we are taking sample size are equal.
Yes. All the
Okay.
samples should come at the same gap, after the same gap. So
Okay.
after same amount of time. So for that you need the my colleague will discuss that how to make things at the like uniform sampling, how to make the sampling at the uniform. Okay. Now what is the LQR control technique? In LQR control technique, basically it is an optimal control technique where we have some cost function, which we call as the cost function, which is our the things which we have to minimize. Basically, any optimal strategy means minimizing some performance indices based on your system. Okay, so here this we have to minimize this cost function j, which is given by this integral, which is 0 to infinity x transpose qx and u transpose ru. Now what is q and r, and what is this? So basically this is the time. So if you see 0 to infinity means this is called infinite time horizon. That is, you want to achieve your infinite time horizon. If there would, instead of infinity, if it would have been t, sometime t, then this would have called finite time horizon. That is, you want to achieve your optimality in a fixed time interval, or you want to achieve it in like in infinite time. Okay, so that then the optimality quadratic function becomes the infinite time horizon or finite time horizon. Now LQR stands for linear quadratic regulator. Okay, these are the three things. What is linear about this control technique? The plant. You have designed your plant, you have linearized your system, so the system on which you want to implement this technique becomes linear in nature. So that is the first L. The next is the quadratic. What is quadratic about this? The function, the optimality condition which we want to minimize is quadratic in nature. Basically, Q is your diagonal matrix. So like say if X is x1, x2, let's say there are two variables, and so X transpose becomes x1, x2 row matrix, and Q is some Q cross 2, let's say q1, 0, 0, q2. This is your diagonal matrix Q. So now what is the, if you just do the mathematics, this will become q1 x1 square plus q2 x2 square. So now see this, these are quadratic in nature, and q1 q2 are the weights you are deciding on those quadratic functions, that what weight is given to which state. Correct? So this is basically quadratic cost function. Similarly, U transpose RU, if you have like multiple inputs, usually we in our cell balancing robot, we usually have a single input system. So we take R as 1, or you can take any value of R, which is a scalar right now, but it can, like if you have 2 or 3 inputs in the system, then this R can also become matrix. Here in our case, we are taking this R as a scalar 1, simple, plain. So it will become RU square. Again, it is a quadratic. So some summation of quadratic functions. That's why this second Q, which is quadratic cost function. We have to minimize this particular thing. Now, regulator problem means the desired variable should go to 0. So taking it to 0 is our desired goal. So that is called the regulator problem. There is a counterpart which is known as servo problem, where we basically have the reference tracking. So we'll not go into that. So LQR control technique basically means that solving a regulator problem using a linear plant and a quadratic cost function. Understood? Now, how we choose Q and R metrics. Now, Q and R metrics basically depends on our performance objective. Like we have X, theta, C. I don't remember the order, so I'm just taking random order. But when you will be designing the controller, you need to be very specific with the order of the system which you are taking. Like states, order of the states is very important, because metrics will change accordingly. Like these are your X. Now, if you talk about the inverted pendulum, what is your primary objective? To balance it in inverted position, correct? Now, balancing it in an inverted position precisely means that your theta c should be 0. That is the primary objective. And theta c double dot should also be 0. So the most important is your theta c should become 0. The second most important is theta c dot becomes 0. Third most is theta w dot becomes 0. So first important, second preference, third preference, and this is like least preferred. Even if theta wheel does not go to 0, doesn't matters much. Fourth priority. Now, whichever is the highest priority to you, you want to apply the maximum weight to it so that it is achieved by utmost accuracy. So based on your objective performance, you will choose Q1, Q1, Q2, Q3, Q4. These are like your 4 parameters corresponding to your X1, X2, X3, and X4. So depending which one is most important, you will increase the weight of the Q accordingly. So this is how you minimize the error cost. This is called the error cost. The choice of the Q defines that how you choose the error cost. Similarly, as I told you, the energy provides you with the energy. Input provides you with the energy. So the second term, which is U transpose RU, is known as the energy cost. So there is always a trade-off between whether you want to minimize the energy cost or error cost, which you can minimize more and which you can minimize. So one leads to the other. So for our balancing act, we will remember that this is how we choose the Q matrix. Best. So like first state is very dear to us. We want it to be utmost accurate. So Q1 should have the highest weight. Second should be Q2. Third should be Q4, and the least is Q3. You can take the least value for the Q3. So similar, this is the way how we choose the matrix Q and R. Now to end my part, I will just present to you with a simulation, which you can see. Pandey, I want to stop. Sorry. Yeah. So with the simulation, which you can see. Yeah. So I have already written function and I'll just run it for you. So you can see that this is my A matrix where my theta c is the third parameter. So you can see that it only depends on the theta c. So my value is like theta w dot, theta w dot, theta c and theta c dot. These are my states. Okay. Now B matrix is like, again, you see the states. Now Q, if you see, theta c is the first variable, theta c. So I have kept the highest weight on theta c, that is 50,000, and theta c dot, which is the third parameter, I have kept it with the second highest. And theta w and theta w dot is like not that important to me, so I have kept equal weight for them. So this is how I chose the Q. Then I got the R matrix. Then there is a function called as LQR function in our MATLAB or Octave, which you can use to find out this gain K. And then you can see that these eigenvalues of the A matrix, which is now after applying the controller, is coming into the negative half of the complex plane, correct? So I'll just run it again. Sorry. And you can see the controller acting on the inverted card pendulum. So you can see the set point as 0, 0, pi 0, because I have taken the reference point from the bottom vertical vertical. If I would have taken it from the top vertical, it would have been 0, 0, 0, 0. So y set point can change depending what is your reference point. So yeah, so this is the demonstration. Now to move ahead with the CoppeliaSim and how you choose the right hardware for you. The session will be taken care by Avijit Pandey. So over to you, Avijit.
I'm having some problem sharing my screen. Just wait a second.
So we are facing some technical difficulties right now. So just bear for 2 minutes. We'll be joining soon. Avijit will be joining soon. They will be taking over. Meanwhile, if you have any question, you can ask related to our first session which we have had till now. Ruchi, I think this is streamed online or not on YouTube?
Yes, sir.
Yeah, so I don't think that we need to share the PPT. You can get it, the content from the YouTube. Ruchi, I think Abhijit is not the presenter. You can make Abhijit presenter.
Sir, which device? Avijit e-Yantra MacBook is a presenter. Can you check, sir?
Okay. So any other question apart from the PPT? I explained it. You can get it from the YouTube live. The content you can get.
Hello, sir. Hello, sir.
Yes, yes. Please go ahead.
Yes, sir. So I have one question that if we consider the weight criteria, like I want to send 1 kg weight from one place to another place. So it is more easily possible to PID robot or balancing by reaction wheel robot.
Look, there is no like straightforward answer to that whether PID is easy or LQR is easy. For PID, without knowing anything about the system, you can design the PID control technique. That's the best part of the PID. So if you don't want to model the system, you can easily do it with the PID. But for LQR, you need to have a model first. Once you are having the model, with the LQR control technique, the tuning is very easy. Like you add certain weight, then you just add feed that weight into your system model, and immediately you get a new gain matrix K, and you can then stabilize the system. So tuning of the system becomes very easy with the LQR control technique. The system takes care of, your model is taken care of. In PID, this becomes very difficult that you don't know the system. As soon as you change certain parameters of your system, you have to retune your PID control. Okay, so how to define easiness is something of question. Whether you want implementational easiness or you want to tuning easiness of the tuning. For the tuning thing, LQR is better, but for applying the control technique itself, PID is better.
Okay, sir. Thank you.
I think Avijit is now able to present his screen. So we will move on to the Avijit. Avijit, over to you.
I think I'm audible. Yeah, okay. I hope there's no echo. Anyone can confirm? Hello.
Sir, there's no echo.
Okay, good. So good afternoon, everyone. Thank you for joining today. So let's continue the discussion. So we have seen how the robot should be modeled, how the gain matrix and everything can be calculated. So before implementing anything on hardware, we can first try to simulate the same thing in some sort of simulation software. And one of the best free open source software of them is CoppeliaSim. So you can just go to coppeliarobotics.com and download the free educational version for it. And let's see what elements, what basic elements are there in CoppeliaSim, and we'll do some practicals about it. So first of all, let's talk about scene. So we'll talk about scene, we'll talk about primitive shapes, joints, and hierarchy. There's something called hierarchy in CoppeliaSim, then scripts, and how we can have complex shapes also. So everything in CoppeliaSim happens inside a scene. So when you open CoppeliaSim, you'll be given a new blank scene. In this scene itself, you import elements, and then you write code to make that element behave in certain way. Okay. Or did someone say anything? Okay, I'll move on. So this is a basic setup that you can see here. So inside the scene, you can add elements. Those elements can be active elements like joints, or some sort of mass like shapes. So there are 5 primitive shapes available: plane, disc, cuboid, sphere, and cylinder. So whatever you want to design, you can design using by combination of these primitive shapes. And to actuate, to do some sort of actuation, you can use joints available in this CoppeliaSim. There are 3 types of joints: revolute joint, prismatic joint, and spherical joint. So revolute joint is basically like a motor, or something which creates a rotational motion between 2 objects. Prismatic joint is basically a linear actuator, and there is a spherical joint which has a 4 pi rotation capacity. So it can rotate in any direction, in any orientation. So using a combination of these, you can create your own structure. So I'll show you an example of it. So you can see here that we have created one self-balancing robot, just like the biped petrol theme. So you can see there's let's see. Okay, so here you can see that it is made up of combination of different primitive shapes. So there's a cylinder, there are vertical cylinders also. Then there are cuboids, the 3 cuboids with 3 layers. So this is basically representing a physical structure of the robot. Then so this is like physical structure using primitive shapes. Then there is also wheel, that is also a type of primitive shape. And what is placed between the motors, cylinders representing motor, and the wheels is a revolute joint. So there are 2 revolute joints representing 2 motors, and these they have certain properties. You can play with them. So I'll show you some of these. So you can have a maximum target velocity, maximum torque. You can also set a PID, which is already available in the software itself, which will help you control the angle of the motor in a certain way. So all these features are available for different joints. So using a combination of these primitive shapes and joint, we can create a self-balancing system. But just adding these things into a scene will not result in a successful system. You need to have a hierarchy. What hierarchy means is that everything should come in particular order. So suppose this is the basic structure. If this is the basic structure, then motor should be placed as a child of this body. So what the child means? So there's a parent-child relationship between objects in CoppeliaSim. So there will be one object which will be a parent, and further down the line, its children will come. Okay, so the motor should act as a child of the physical structure, so that wherever the parent goes, motor will stay stationary with reference to the parent itself. Okay, so basically you are connecting the motor to the body. Okay, and further you need to make the wheels as a child of the motor, because we don't want the wheel to fall off from the motor. So as the way the motor rotates, in the same way the wheel will rotate. So let me show you what will happen if you don't have a parent-child relationship. Let's see, let's make them independent. Okay, so now we have base, body, wheels separate, motor separate, everything else. Right? When I play the simulation, everything like shatters. Things are not connected to each other. Okay, so I'll just undo everything. Yeah, so that is why we need to have a proper hierarchy while designing the robot in CoppeliaSim. So why do we do that? Why are we designing? Why are we taking so much pain to design something in CoppeliaSim? So to validate our controller. So in CoppeliaSim, lot of things are done easy for you. For example, what will be the where will be the center of mass of the body? What is the total mass of the body, and how the bot will respond to the controller tuning parameters. All those things can be easily tested in a simulator. Further, because while implementing it into hardware, other problems will also occur that you'll have to face. So before tackling those problems, let's first make sure that our controller is proper. So how do we write the controller in CoppeliaSim? So once you have created the whole structure, the hierarchy, you can add scripts. The scripts are lines of code that you can write in CoppeliaSim, which will act as the coding to your robot. So these scripts can be written in multiple languages. So there are inbuilt scripts, inbuilt languages like Lua and Python. And you can also have remote API languages like Python and C++ and C. So for the beginners, Lua can be very easy. You can just add scripts. You can just click any element and go to add section. And in the script section, you can add threaded and non-threaded Lua or Python script. Okay. So once you add the script, these scripts will be run when the simulation starts. Okay. So apart from that, there are also scripts called customization script, which will run immediately as soon as the scene is loaded. So whatever is written in this particular script will be coming into action when the simulation is started. But whatever is written in the customization script will be immediately started as soon as the simulation, as soon as the scene is loaded. So this you can clearly see that this, can you see this plus kind of structure representing each axis? This is representing where the center of mass of this robot is, and this is being done by a customization script. Mind this, that simulation is not running yet. This script is doing its job, showing me what is the total mass of the body and where the center of mass will be. Okay, so let's run the simulations, and so you can see like it's balancing properly. So let me give you a close up. So I think you can see it's slowly rotating, trying to keep itself upright. So this is how you can ensure that your controller design is proper. Okay, so you can so suppose you have created a physical structure, you can do you can create the same physical structure representation in the CoppeliaSim and see where the CG will be, what will be the mass, and there you go. Then you write your controller and you can verify it. Okay, let's see. Okay, let's say if I want to have complex shapes, because not everything can be in this plate and cylindrical structure. Okay, so let's say you have some sort of curvature or some combination of complex shapes. So for that, you first need to build those shapes into some third software, like Fusion 360. And from those softwares, you can directly export the 3D mesh that you will be including into the CoppeliaSim. So I have some 3D mesh already created in Fusion 360. I'll show you how you can, once you have created those 3D mesh.stl files, how you can include them into the CoppeliaSim and make use of it. So let's go to import and import a mesh. So I have these 3 STL files I have. So when you include those STL files, they might not be up to your expected scale. For example, in this case, you can see that they are huge in size. Like it's hard. Like CoppeliaSim is having problem to show them all at once. So what we can do, we can resize and reshape everything. So what I'll do right now is scale down the size. I'll scale it down every one by 10% or 1%. Do this one also. So while scaling down, you are basically reducing the footprint of the shape that you have imported. Okay. Okay. Now you can see that it's a shape of a car. Okay. So just like that, you can import different shapes in your CoppeliaSim. And suppose if I am trying to make a car in this simulation, I need to attach these wheels also to the car, right? So you can rotate objects, move objects within the scene. So for in this scenario, you can see that I need to rotate the wheel and make it aligned to the wheel shape of the car. So what I can do is like rotate this particular element according to y-axis, in the y-axis by 90 degrees. So you can do the rotation by mouse also, or you can do the rotation by the number also. So you can just put in the number how much you want to rotate it and just press enter. In the orientation, you can do that. In the orientation section, you can directly set the orientation. In the rotation section, you can set how much rotation the object will take in which axis. Let's see. Let's move this. Let's move it a little up. There you go. So like this. Okay. So you can see that I have these two shapes, but I have not made any hierarchies. What will happen? Oh, I have not made them. Okay. So let's make them respondable and dynamic. Okay. So you can see that it's falling apart. It's not making any sense, right? So for that, you need to have a hierarchy. Flow is not responding. Okay. So once this is done, you can start writing your controller accordingly. So this is basically done mostly to beautify how the system is looking. I'll show you one example. So if you see, you can see like very beautiful looking systems, but when you look into it, actually they are like made up of primitive shapes, but in externally they look very different kind, because these mesh files are written on overlapped on these primitive shapes. Okay, so once you have verified your controller, you can move on like implementing the same thing in hardware. So in the hardware section, we have microcontroller, which will basically control everything. It will take data from the sensor it will communicate doing some through some communication module, and then it can just send the signal to the motors in order to like do the proper actuation. So in this section, we will talk about three parts: sensors, motors, and communication module. So okay, so usually for cell balancing systems, we use a sensor module named GY87. It is basically called inertial measurement unit, IMU. Okay, it has an accelerometer, a gyroscope, a magnetometer, and a pressure sensor. So it has multiple sensors within the sensor module. Let's see what do they measure actually, and which of these are actually useful for us. So accelerometer is responsible for measuring the linear acceleration. So if you remember, in CoppeliaSim, we can directly measure the angle of the body just by writing one line of code. Let's see, I can show you. Yeah. So when it comes to measuring the angle of the body, just these two lines are sufficient for measuring the body angle. But it is not that easy when you are doing that in hardware. Okay. So there you will use different sensors to get the and combine value. There you will get data from different sensors and combine those values to get the actual orientation of the body. Okay, so accelerometer measures the linear acceleration. So this is basically measuring the acceleration due to gravity, and in a particular axis direction. And when the orientation changes, that resultant value is changed based on the orientation, and that is reflected through the accelerometer readings. Then there is gyroscope. Gyroscope is basically responsible for measuring the angular velocity. So it's mind this, not acceleration, nothing linear. It's basically measuring the angular velocity, how much, at what rate the object is rotating. So what we do, similarly, magnetometer is pretty evident in itself. It measures the orientation of the sensor with respect to Earth's magnetic field or any strong magnetic field around it. So mostly it is referring to the Earth's magnetic field, unless there is some better or higher intensity magnetic field source. Then there is a pressure sensor, obviously measuring the atmospheric pressure. So in this particular application, we usually use accelerometer and gyroscope. So how do we use them? So accelerometer is a device which is giving us the linear acceleration data. So if the bot is tilting, the acceleration on a particular acceleration due to gravity on a particular axis will change. And gyroscope is doing the giving us the angular velocity. Okay, so what happens in reality? These sensors are not noise free. Nothing is noise free in reality. Okay, so to eliminate those noises, we implement some types of filter. So accelerometer data is very for accelerometer data we implement low pass filter, and for gyroscope data we implement high pass filter. And at the end, we combine whatever reading is taken from the whatever reading is coming out of those filter using a complementary filter. Okay, so why low pass and high pass to a specific sensor is because gyroscope data is very accurate in nature, but it has a drifting effect. So suppose if you change its angle, change the angle of the sensor, it will give us a proper value. But once you stabilize, slowly the gyroscope value will keep on drifting. So in long term, the gyroscope data is not trustable. So for short term, we use gyroscope data, and for long term, we use accelerometer data. So that's why low pass and high pass filter. So after reading those values, we combine the gyroscope angle and accelerometer angle using a complementary filter. So once you got the angle, basically you measured the state of the body. Okay, but you have measured the state in terms of the orientation of the board itself. But there are two states also: the angle of the wheel and angular velocity of the wheel, right? So for that, there is something called Quadrature Encoder embedded in motor. Most of the motors that we use, we have them with loaded them with Quadrature Encoder. So what is a Quadrature Encoder? It is basically a slotted disk which has two sensors, which is passing through two optical sensors. So every time a slot passes, a pulse will be generated. Okay. So these pulses on both. So there are two optical sensors. So every time a slot passes, two pulses will be generated through two different optical sensors. These pulses are received on different channels, channel A, channel B. What you can clearly observe here is that they are not in phase with each other. So if slot is passing through A, it will not immediately pass through B. Maybe it will, after it is halfway passed through A, then it will start entering into slot into the area of the second sensor. So what it gives us is basically a set of two pulses, and combining them, we can have multiple observation for one particular slot pass. Okay, so suppose if you are just looking at one channel only, what we can see is that every time one rising edge is detected, one slot is passed. Okay, like here and here and here, right? So you can see that in this this section is basically representing the same thing. Or what we can do is that we can look at the same channels, both rising edge and falling edge also. So what will happen? Within one slot, we will have two pulses, rising edge and falling edge. Okay, an event detected at this point and event detected at this point. Okay, so from one channel we can have two events. So if there are two channels, we can have total 4 events for one slot pass. So suppose there are 360 slots on the disk that is rotating. So what will happen? We can have a resolution of 1 degree per slot, or half degree per slot, or 2.5 degree per slot. Okay. Okay. So suppose here's an example. So suppose there are 250 slots in the disk. So how, like, just try to calculate. So divide 360 by 250. So the first scenario is basically giving us the resolution of 1.44 degree. In the second scenario, where we are detecting both rising edge and falling edge of this one single channel, we will have a resolution better than that, 0.72 degree per pulse. Okay, so this is for 250 slots. So suppose there are 1000 slot or 100 slots, accordingly it will change. So basically we are dividing 360 by that number of events that we can detect within one slot pass. Okay, so if we are doing into the quadrature mode, so we will have a resolution of 0.36 degree per pulse. Okay, so now through this we can measure the wheel angle and wheel angular velocity. So since we have measured angle and angular velocity of both body and wheel, we need to implement this into a controller. So usually we have microcontrollers to do this part. So microcontrollers are basically small computers which have a microprocessor and a small microprocessor on it, along with the RAM and some storage unit and different circuits like timer circuits. So timer circuits and analog to digital conversion circuits. So just like if you remember, a few minutes ago, Avinash told you that we need to have a fixed sampling time. Okay, since things are digital, we need to have a fixed sampling time. So while implementation, how do we ensure that the sampling time is fixed? That at every 10 milliseconds, the reading is taken and the actuation is done. So for CoppeliaSim, it's very easy. You just set this DT to 200 millisecond, 9 millisecond, 50, 25 or 10 millisecond. But in hardware, you need to do that using in microcontrollers, you do that by using a term called timer ISR, timer interrupt service routine. So there are timer circuits in Atmega microcontrollers that we mostly have, mostly use. In Arduino Mega and Arduino Nano and all those have Atmega microcontrollers. So what these timer circuits do is that they keep count of every passing second. For example, so if a timer has a resolution of 1000, so within 1 second it will count 0 to 999. It will do 1000 countings. Okay. So based on this counting behavior of timer, we can ensure that, okay, if I want to have a 10 millisecond service routine, I need the microcontroller to count from 0 to 9, that is 10 millisecond, and do some action. And after doing that action, again count from 0 to 9 and do that same action. So that is done using timer interrupt service routine. So these ISRs, okay, so what do we do in ISR? In the ISR only, we take the readings from the sensors. So every time I want the reading from GY87 or the quadrature encoder of the motors, I will do that using, we do that within the interrupt service routine of that timer. Okay, it can be executed based on the, so we have to do some setting in the timer registers, and based on those settings, it will count for a fixed interval time and execute a certain code. Okay. Okay, so this is sensor data. So before, so okay, let's say we are getting all the sensor data, we're getting all the values, but at the end of the day, motors are responsible for doing the actuation. Okay, they are the elements that are applying torque and creating a velocity and acceleration, due to which the robot is going to balance itself. So how do we find the motor with the just right amount of torque in it so that it can balance the robot? So for that, there's a very simple funda we can use. So we know, can I use, let's see if I can use a pen here. How do I use pen in this? I can't. No. Okay. It's okay. So what we need to do is that suppose wait a second, I need to show something. Okay. Imagine a pole with just give me a second. I'll find a way to present something. Okay. So suppose this is the pole, this is the motor, and this is the mass. Okay. So when the robot is tilted like this, at that moment, we will have the mass will exert there will be a force acting downwards like this, and there will be a particular amount of torque requirement in order to bring this element back to the upward position, and that amount of torque will be decided based on the angle that body is making from the vertical. Okay, theta, which is basically one of the states. Okay, so in order to find the right amount of torque that is needed, we need to first set a limit that if my robot can recover itself from plus minus 5 degree or 10 degree. So once that angle is defined, then we can easily find out by this function, simple math, by this function, that how much torque will I need in order to balance the robot using a particular motor. So that torque can be found using this equation. Okay, where m is mass, g is acceleration due to gravity, L is the length of the distance of the center of mass, and theta is the angle. Okay, as simple as that. So you need to first find out the sensors, first find out the states using sensors, then you identify the right motor. So there are two ways you can go. Either find a motor and know its torque, and based on that you design your robot, or you design your robot and find the maximum required torque, and based on that purchase a motor which has the sufficient torque according to it. Okay, so so this is, you are doing all this, but somewhere along the way we missed one thing, that is the communication. So how the microcontroller is reading data from the sensor, how the microcontroller is sending the data to laptop or some third device to display it, all these things, how the microcontroller is taking taking input from the remote controller that you have. For all these purposes, we want to have a communication method. Okay, so most of the sensors that these days, they come with the I2c communication module. So I2c is basically inter-integrated circuit, full form of I2c. So it's a two-wire interface. So there is one wire called SCL, on which the clock pulse is provided to the sensor, and another wire which is called SDA, on which the data is transferred. So in this I2c communication method, the data can be transferred from microcontroller to sensor or sensor to microcontroller. But there is always one device which is called master device. In most of the cases, it is the microcontroller itself which is the master. And microcontroller just sends the signal to slave device, which is the sensor. Okay, give me data now. So you remember we were talking about fixed time interval, taking data at fixed time interval. That is how we do it. At fixed time interval, we give signal from master to slave that, okay, give me the reading now. Okay, so this is called I2c communication. What is beautiful about I2c communication is that on the same two wires, SCL and SDA, multiple input devices can be connected, multiple sensors can be connected, as much as you want, like 2, 3, 5, 10, 50, whatever you want. Why? Because every sensor will have its own address, and when microcontroller wants data from a particular sensor, it will call that sensor by its address. So other sensors will stay inactive, and only the sensor who is called will send the data to master. Okay, so this is the beauty of the I2c communication. Apart from I2c communication, we also have serial communication, but this is the advantage in I2c communication over serial communication, is that we can have multiple devices connected to the same line. So for example, if you go and read the data sheet of Atmega 256, you will find that there are 3 serial communication channels, but there's only one I2c communication channel, because we only need one, since we can connect as many sensors as we want. However, let's talk about serial communication. So in serial communication, there is TX and RX. So there are 2 devices, just like I2c. So there's a transmitter device and there's a receiver device. So there are 2 pins on each side, TX and RX, and they are connected invertedly. That means TX transmitter of one device will be connected to the receiver of other device, and vice versa. Okay, so in this communication method, we need, so unlike So for example, in I2c, there's a pin called SCL. So this SCL pin in I2c is providing the clock to the sensor itself. So there we don't need to define at what rate the communication should happen. Whoever is familiar with communication system will know that for the communication to happen, we need to, both the devices should operate at but synchronized frequency. Okay, or the data in order to have asynchronous communication, we need to have some sort of marker. So in serial communication, we set the baud rate, something called baud rate. So through setting the baud rate, we will know that both the devices will communicate at this rate of communication, okay, at this speed. And so serial communication is basically wired, but since we want our robot to be wireless, we can convert that wired system into a wireless system by using a tool called Zigbee Module. Okay, most of you might be familiar with this. So Zigbee Module is basically a serial communication device which will take data from microcontroller and transmit it to another Zigbee module, which is connected to your laptop or some third microcontroller. Okay, so this way you can do a wireless communication between two robots very, very easily. Yeah, you can, if you don't want to have a remote, you can just transmit data on serial communication using keyboards. So if you have played games in your childhood, the W, S, A, D are used like function keys for forward, backward, left, right. Something similar you can build for your own robot. So yeah, so since we have been talking a lot about self-balancing robot, let us show. You can show that. Let's see if it is in view. I'll stop sharing. So that is it from my side for the serial communication and hardware stuff. We'll see a demo. It's not looking good. Excellent looking, sir. Hold on. You disconnect. पिन कर दीजिए इसको. How do I pin this? I think you can hear us. So you can just pin a widget e-Yantra iPad to your screen, and you can see this that we have a one self-balancing robot here. It has whatever we have been talking about is implemented in this system. So we have motors with some gearbox here, you can see. Then there's battery and motor drivers. So obviously motors cannot be directly driven using the microcontroller because they draw too much current. So for that we have motor drivers. Then at the bottom of the top layer, we have sensor, which is actually the GY87, which is measuring the angle and angular velocity of the body. And motors here are encoded, Quadrature Encoder enabled. You can see this black part. It is the sensor for the motor. Okay. And once we turn on this robot, what it will do is it will take data from these two sensors and it will try to balance itself on the vertical axis. So right now it is trying to balance, but what you see here is that one of the motor is not properly actuating. So this is the such problems will appear when you go into hardware implementation. So since one motor is actuating properly, another is not up to the mark, what you need to do, you need to take care of these things using coding implementation. So in order to make them behave equally, we need to scale up the signal that is given to the motor which is not actuating properly. Okay. So since this motor is not working, it is not giving the proper actuation on the both sides. Okay. I think that is it from our side. Any question and any doubts, please unmute and ask.
So can you repeat how many sensors you have used? One angular sensor and the other one is?
So one sensor that we have used is GY87, which it is not a sensor, it's a sensor module. So that GY87 has a gyroscope and accelerometer inside it. And further, the motors have a quadrature encoder in it. That is also a type of sensor which is giving us the rotation of the wheel and its rotation and angular velocity. So
Okay,
we
sir.
measure rotation and calculate angular velocity. Why someone asked why we need wheel encoders. So we need wheel encoders so that we can measure at what rate so we give, let's say we give 12 volt to motor, but we don't know at what speed it is rotating, or we give 10 volt or 5 volt, so speed will change, but we need to know at what speed it is rotating in order to have the LQR implemented, because the LQR controller that we have designed is taking wheel angular velocity and wheel angle as input state. Thank you. Any other question, please?
How long it took to build? Can you please tell from?
So we have built this system like long ago. We had themes based on this in EYRC. So in 2016 we had a theme. EYRC 2016 we had a theme where students built a self-balancing robot using PID controller. Then in 2019, EYRC 2019 we had a competition. We had a same theme implemented but with LQR controller.
Thank you.
Basically, the controller was not LQR. It was given the choice that
students are given the choice if you want to build using LQR or if you want to build using PID. And almost half of the finalists did it using LQR and half of the finalists were using PID. So these were like BTech students. So it usually it takes a month or so if you want to build a fresh system. Since we have understood the motors and everything else, we have codes, then it does not take much time for us. But if anyone wants to build from ground up, 1 month, 1.5 months should suffice. How can we add pick and place function? So that's a very interesting problem statement. So in order to do a pick and place, so two methods we can do a pick and place method. So one, in fact in biped petrol theme in EYRC 2019 we did a pick and place method, but we did the pick and place using the electromagnets. So there was no moving component there was no moving arm on the robot. But if we were to add a moving arm on the robot, this will pose a different challenge. Why? Because when the arm is moving, the CG of the bot is shifting, and the controller is designed for a particular CG position. Okay, so when arm is moving, the CG will change, the controller requirement will change, K matrix should change. So in order to have a moving arm, we'll need to move from microcontroller to microprocessor, which will continuously calculate K matrix and implement accordingly based on the position of the arm and shifted CG. I think does that answer your question, Dr. Pallavi?
Yeah, sir.
Okay, thank you.
But sir, what type of means electromagnetic induction means we can use only
So
a particular materials only. We can pick the particular materials.
Right. So what we did is like there were blocks with metals inside it, and the robot went to the block and just activated the electromagnet and grabbed it and kept it there. It did not change the position. But in ARM thing, you can just pick it up and store it in one storage area. So ARM has its own benefit, like you can pick up multiple objects, but then the problem statement changes from a fixed linear optimal control system to what was the second one? Robust control system. Because the CG is changing, the noise is added with every added element.
Then even sir, we have to change the DOF of the robo also. And that would again it is a different thing now, sir.
Even on the same robot, you can add ARM. Degree of freedom will remain same for the motion part, definitely.
Okay, sir. Yeah, thank you, sir.
Can we get this recording for future purposes? It will be available on e-Yantra YouTube channel, so you can refer to it. Is compilation tool open source? Yes, it is open source. So it has 3 versions: player, pro, and educational version. Education version is free for all. Let's see. Why we should use self-balancing robot? Avinash sir, would you like to answer that? Why do we use self-balancing system? What is the need? I think it's typing something. Okay, Shrikant's, Gokul's questions will be answered by Avinash. I'll move on to next question. Can you explain how to code? Because that's important. Okay, so for hardware coding, it's very recommended from my side that you use Arduino. And for this particular sensor, which has MPU 6050, the GY87 sensor, it has a MPU 6050 sensor, which is accelerometer and gyroscope. For that, you will get a library easily online. So for Arduino coding. So once you use that library, you don't even need to implement any filter or anything. Just read the data, sensor data. For particularly reading the sensor data from the wheel, you'll need to use the interrupts. So using Arduino, you can do the coding very easily. If you want to learn, you can participate in EYRC this year. We have a theme called Delivery Bike, which will not exactly work on the same system. It is basically creating a self-balancing bicycle using a reaction wheel. But most of the fundas that we have implemented in this system will be implemented on that system also. In fact, that will have more learning to do, because the reaction wheel balancing itself is a different domain. So there you will learn coding on the hardware also and simulation also.
So coming to that question of
why
we
mute.
use.
आप म्यूट हैं. अच्छा, इधर से ठीक है.
I'm audible, right? Yeah. So
Yes, sir.
Why we use self-balancing robot is like a question which is you can question things, but industries are using it in the inventory management and whatever advantages you can have, like maneuverability of the robots become easy, and it can move to different terrains. So these are like added advantages you get when you move to a self-balancing robots. Although it is inherently stable, but via coding you can make it stable. So that's not an issue. It gives you an added advantage, similar to what we have the advantages.
Also, you are decreasing the number of actuators in the system also. So the four-wheel drive system is going to cost both economically and energy-wise also. Can different amplifier be used instead of low? Sure. So a lot of people implement Kalman filters also. So it depends on how you want to work with sensor noise. So GYT7 particularly has a filter in itself only. So it filters, it gives a noise-free data, very much noise-free data. But if you want to implement certain amplifier, you can filter, you can go ahead according. So it's all coding. There's no hardware required for that. Last year, Dairy Robo theme, it's self-balancing, moving and delivering item, pick and place item. Yes, but it was in simulation. So as I told you that things are very easy in simulation because there's no noise coming to your system. The sensor data, there's no sensor because the direct variation you are getting, and motors are ideal in nature. Whatever torque you tell to create, it creates that way. So simulations are easy, but it is a necessary initial step. But when you come to hardware, this year the delivery bot is based on dairy bike, and but it will not have lot of moving arm thing because that's the reason I told you earlier, changing CG and dynamic body behavior.
Answering Neeraj and Sainath both answer. It is mix of both. You'll be taught everything, but you will have to learn on your own also. So it is a mix of things. And Sainath, if you want to learn balancing bicycle or something related to balancing, you should definitely participate in the e-Yantra robotics comp.
Okay, EYRC is launched, guys. I want to just put focus on EYRC for a minute. So most of you are familiar with EYRC, but for our viewers who are watching us on YouTube, e-Yantra robotics competition is a method to learn different technologies in field of robotics. And every year we organize it for college students, all the graduates and undergraduates. So be it Polytechnics and undergraduates and diploma participants. And we have been getting participants from across the globe. And this year we have launched the registration, and until 10th of this month you can register and get early bird discount also. And through this EYRC you get to learn and compete also. So in the initial stages we will give you all the necessary content for learning the technology, and we'll tell you what is the problem statement and how you can solve the problem statement. This is how EYRC goes. Sure, we'll give you a link of EYRC registration in the chat. And so this is how EYRC is done. And we have had lot of participants from very remote colleges of the country, and they have been performed. So basically you don't need to have a lot of technical understanding or to participate in this competition, because we tell you everything from scratch. So if you want to learn control, control system, we tell you what is state space modeling, how to do mathematical modeling, how to implement calculate K matrix in Octave. We'll give you problem statements. We'll give you practice sessions. We'll do live session and everything. I think it's time for quiz. Good reminder. Thank you.
I request everyone to wait for quiz. Before the quiz, let me just close the session. So thank you, Avinash sir, and thank you, Avijit sir, for the wonderful session. And thank you all the participants and YouTube audience who have watched our session. Hope it was informative. Thank you, everyone.
So while Ruchi is posting the quiz link, there's one question: how can I use Python language in CoppeliaSim? There are two methods for using Python language in CoppeliaSim. So earlier only Lua was available as the inbuilt API, and Python can be used as a remote API. But in this new update, Python can be used as an internal API or